ready to start lecture 6 next time. But this bottom part of lecture 5 is a neat thing that you should see, because it has, again, wave analogies. That means it's analogous to some classical phenomena known very roughly as quantum chaos. But it's something that starts in the very beginning, the most elementary quantum mechanics that most people get in sophomore physics is imagining a quantum particle, that's a wave, going around a ring. I call it the Bohr ring. It's the Bohr atom before he branched out and made it work in 3 dimensions. So that particular system, you would think, oh my gosh, it's so simple, it couldn't do anything interesting, could it? And the answer is it can be very interesting. And so what we're going to talk about is what I call the tiny Big Bang, and that's where you take a Gaussian wave packet that's fairly narrow or very narrow, depending on how much you can stand of this, and you let it go. And it makes a quantum fractal. We were the first to discover this numerically at Los Alamos in 1980. And we are also the first to really have a neat theory for it that's based on symmetry analysis and also mimics this problem. And this is a ghastly problem for whoever might be stuck there. But the idea is that we're going to take this poor little M2 here and make it insignificant mass compared to M1, who is a ball moving in at a linear velocity. So it's the extreme case of what we were treating already as we made the ratio M1 over M2 bigger and bigger and bigger, or the ratio of M2 over M1 to approach 0. So that's what we're going to do. We're going to do it geometrically. That means I have to find some graph paper for you, because we're going to do the detailed graph of this collision, just its trajectory in space and time on the board. And if you could reach back, Al, I think there's some graph paper there. So we're going to need this thing held horizontally so that you get 8 inches to play with horizontally. And mostly rulers are all that's needed. Now I'm going to put both of these screens on this particular subject right here. All I want to do is construct the trajectory of the little mass as the big mass, whose front end is right there, comes in, hits the little mass, and knocks it forward. Starting at velocity 0, it will, as we have shown before, pick up twice the velocity of this ball. This ball is coming in with V1 equal to 1. So we have a slope 1 line moving this way. If that's positive x, it's the velocity, unit velocity. So what I would have you do is on graph paper, and I have not yet put the coordinates on, but you have to put them on, so you can put them on there with me. From some point here, draw a slope 1 line to the left, and it wouldn't hurt to also draw one, just a very light one, to the right. So I'm going to go ahead and put that in too, using the graph. But let's look at the units. Do the units so that you can get 8 inches. This will be the spatial distance. If we're going to call this the origin, the crunch point, then this would be -1. This would be -2 right here. This would be -3. And -4, we're not going to have much going on past -3. And then this will be 1 unit of time. Might as well call it -1. This is crunch -1. This is crunch -2. This is crunch time -3. And the ball shows up on the plot here at crunch time -5, actually. Here's -4, and -5 is off the board there. The big ball front end shows up at -4 and is still not hit the mass that's coming down with no speed at all.
Dr. Harter?
Yes.
What are the x and y axes? Like y-axis is...
This is space.
Okay.
This is a, let's just label it what it is. It's a space-time x versus t, or t versus x. Probably a better way to write it would be t versus x. As it's oriented here, it's a Minkowski as opposed to a Newtonian.
So y-axis is time, right?
And this is time, yeah. Negative time, we're counting backwards from the big crunch, okay? So minus time axis.
Okay. So, physically we have an inelastic collision, and we try to analyze it backward, like after the...
Elastic. Elastic.
Oh, elastic, oh.
Yes. What we're good at. We're not so good at inelastic. You remember that that's the real world, and we're very pure here at this point. But anyway, this is the space coordinate down here. X. Space. Also measured in distances from the crunch point. And rather than use that, I use a regular ruler. Here comes the small mass. And at this point, I've really idealized this. I really would think of the mass as a point. So at t equal -4, this point mass is right there. And then a very heavy point mass is right here. So this is M1. But the way we're using our simulations, of course, this is a monster. This is the monster ball. If you were to just draw it like a super ball, this is the monster M1. And this is a little M2 who has very little mass and kind of looks like that. This one in our simulations is the super ball. This is the pin.
So, Dr. Harter, so M1 is located at the point of intersection of that 45-degree slope and that vertical line from -4.
It's coming in with a velocity, unit velocity for M1 V1 equal 1, and M2 has 0 velocity. Zero initial velocity. V2 equal 0. And there's first collision right there. First collision occurs at -3 time units. Call them seconds and meters per second if you want. Okay? So the question is, how fast if it's elastic? Where should we draw the next part of the trajectory? And I take you back a little bit in what we've been doing here. I had this set up before, and I've got to find it again. I'm going to look through this thing carefully here to see if I can locate that. I think it was at 18 or so on this particular graph. Yeah, here it is. It's at 8. Okay? Remember this, and I've got it on the board here as well. Remember our V1 versus V2 graph. When we were talking about the super ball and pen, we started with them both having -1 units of velocity. That's this point right here. And we got the number 1 big mass to go to the right, which would be bouncing off the floor in our original thing. So it would have +1, and then run into an object that had velocity +1. See if this is, no, that had a velocity -1. This is the number 2 velocity right there. So head-on collisions we did were that sort of thing. And what we showed was, first, the pen at mass ratio 3 could actually stop the ball completely and throw the pen up at 2 units. But the upshot of all of that analysis was, as indicated in this thing, every time you have a collision with this infinite mass, you're simply going to increase your velocity by 2 times that of the big guy. So here's the M1 much greater than M2 diagram that we used as we began our discussion of potential energy generated by kinetic collisions. The M1 being much greater than M2, that's the situation we're talking about, it corresponds to a momentum conservation line that's essentially vertical and approaching absolute verticality as we make the ratios ridiculously large for this ball. So the idea is that here comes this thing with no velocity at all. It's going to gain 2 units after this collision. And you can see that by just realizing that the infinite slope line is right here. Our initial point is here. We're going to simply bisect, where the center of momentum is going to bisect the interval between those 2. And so this guy is going to get thrown up here. And the speed of the monster is not going to change at all. So it's a really simple case of collisions being taken to the ultimate denouement of a big crunch. Okay, that's what we're studying. It's the geometry of that I want to look at. It shows up in a lot of places that you might not expect it to.
Dr. Harter?
Yeah.
So the reason why the line for representing
The trajectory.
M2, the trajectory representing M2 is 0 is because it has 0 velocity, right? So it's parallel.
Yes.
through the time axis.
This is Minkowski,
Okay.
so you gotta turn your head on the side to
Yeah.
get used to it. In calculus, we always draw the y versus time.
So what is the advantage of using Minkowski graph? Like, so how does it make the analysis?
Well, I'd like to use the Minkowski in a lot of the graphical simulation, simply because you're already used to thinking of objects moving, back and forth this way, right?
Okay.
If you use a Newtonian, you have to turn your head like this in order to, visualize the motion. This is mentioned in the very first chapter, right? That Newton versus Minkowski is an issue that we should deal with. So it's complementary plot to Newton. And we have to figure out how much velocity is this thing going to have. If it were to be totally inelastic, it would simply stick to the mass and there would be the rest of the story, right? If you had a crunch, you're just going to end up on this line, right, forever. But we're going to be somewhere off the line. The question is, how far off? If it were to somehow give it infinite velocity, you'd go along this line, right? That's not going to happen. Momentum is got to be conserved. Okay? So this jump by 2 is the thing that's going to happen from now on to the crunch. We're just going to keep increasing the velocity of the little guy by twice the velocity of the big guy, and the big guy isn't going to change. So we're going to do an arithmetic series. We're just going to keep adding 2. But halfway between the next addition, it's going to bounce off the wall. Okay, and that's what this represents, the wall. All right? So we're going to draw a line at velocity 2 until it hits the wall. Then we'll do an equal reflection back and pick up another 2 units of velocity. And that's what's going on here, is V1 goes to here, okay? Reflects off the wall, goes from +3 down here to -3, okay? And then once again, it reflects off of the center momentum, right? And goes all the way up now from -3 up to +5, right? That's what's shown on this picture here. So I go down, I go up, then I reflect back down to here, and then I reflect off the center of mass back up here. Pick up another 2. Each time I pick up another 2. Pretty easy. It's 2 plus 2. Okay, easy as 2 plus 2. So using your graph paper, you simply want to make something that has a slope not of 1, but of 2. Right? So you measure off on this graph, down 1 over 2, down 1 over 2, okay? Down 1 over 2, or you take, bigger steps than that, whatever. It's linear, so no problem. So we're going to work our way over to here, and then halfway on my units to this. We'll be there at about 2.5. So the next more than 2 units of time, 2.5 units of time to be exact, I'm going to be traveling on this line right here. Now, I'm going to extend this line because the geometry of this arithmetic series is very geometric. Let's go ahead and put the line as it's gone so far to there. I'm going to go ahead and extend it out the back door here. And if you look at the next figure in the text that deals with this, you'll see that we're thinking about this mass actually going between another one coming from the other direction symmetrically displaced. So we make a super big crunch. So there's a trajectory, but I'm going to go ahead and extend it to where it runs into the time of the big crunch. Okay. Now, after you have bounced off at this point, the idea is that you'll come back with the same speed, but negative velocity. So I will be coming back here with a slope of 2 to run into the big ball again, this time at time equal -1. So t minus 1 is when we get our next collision with this. This one I also want to extend.
Dr. Harter, again, so you draw, how do you draw the line with the same slope of 2?
Same magnitude of slope, just a change in sign, right? So here's the trajectory. There's the bang point, and there's another bang point coming up right there. But I want to go ahead and extend that down to, well, it turns out to be symmetrically located, you see, on this graph. Here is +1 right there, and then I'm counting 5 of my units, +2 right there, and +3 right here. And this is what made me think that I really had 2 objects here to make a symmetric collision for this mass. So extend this line and you see this, that there's some symmetry. This thing will hit the big crunch time at exactly below where this one came in, where this one made its first collision. Okay. All right, next step. After we come off of this, and I'll just write on here, add 2, that is 0 plus 2 equal minus, I'm sorry, 0 plus 2 equals 2 here. We have 2 units here. We're going to take the speed that this thing has and attach, reflect it first of all, and add 2 again. So the next thing is going to have 4. 2 plus 2 is 4 units of velocity. So I come down from that point, go across 1, 2, 3, 4. Okay?
Can you just explain as previous step once again? Where you said add 2, 0 plus 2.
Say that again.
The previous step where you have written down add 2, there is 0 plus 2 and...
Yeah, you add, just as will happen in the velocity diagram here, each time I take the speed of this thing and add 2 times the speed of the object that's coming in. So I'm taking this thing and increasing the velocity by twice the incoming. Okay, so the next time I do it, I go there. So starting here, increasing our, around, you know, around the center of momentum, really, but the center of momentum isn't going anywhere. It's always going to be at this point because the other guy doesn't move, or affect the difference between the two. So the next step is to increase by 2 to make 4 units of speed. And so forth. Now once again, I can extend that.
Can you just,
Trajectory.
how did you draw that line, Dr. Harter?
Pardon?
That, yeah, that one, that small line, that, yeah, that one here.
Just count off on your graph,
Mhm.
and that's why I want you to make a big graph so you have a lot of leverage here. Count off some set of units. Could be 1 square, but you can do 5 squares or whatever. And then do 4 times that.
Okay.
This is going to have a slope of 4. Okay? So I've done it with my markings. I don't have a very fine set of graphs here, but I can make use of what I've got. And I just simply mark off 1 unit here, and then I go 1, 2, 3, 4 units to get my next point, and then mark that point down 1 on the graph, and go 1, 2, 3, and 4, and put another graph point. I'll put little circles around the ones that I want and erase the others. So I'm going from this point here, which is located at point, let's see, if this was 1 here and we've got 5 things, this is 0.8, this is 0.75, I think that's right, and so forth. Then I'm going to do the same thing here. So there'll be another point right there, and bingo, this one's going to hit the same point, and so is the one that's coming next going to hit that point. So this is what makes this geometry so intriguing, is its very symmetry. Even if I don't draw this one off to the side like this, it's still something of a mirror, because when I finish with the next collision, it's going to be right along that line right there. Now you have finer graph paper, so you can check that by working your way with a, say, a small graph there, and then counting 1, and then counting 1, 2, 3, 4, and so forth, to figure out where this particular point should hit. But I can tell you the answer already, and it's that right there. I don't need a fine graph. And I'm giving you a problem. One of the things I'd like you to do on the problem is just go ahead and analyze this. A lot of it's done in the textbook, but it's worthwhile you just thinking about why in the world this works. What's up here? So here's the return trajectory with slope. This one has slope. If this is +2, this is -2 slope, velocity. And then that speed gets augmented after it's been reflected with a velocity here equals slope equal 4. So we've gone speed 0, speed 2, and now speed 4. And so forth. At this point, I can't use this graph to count off very well, but given the structure that I know about this, I can finish this graph fairly quickly, although it never finishes. This is an infinite series. The next stop here is on this line. So there's the trajectory, and there's its extension. Roughly, missed a little bit down there. And then that will bounce with precisely the slope 6. This one right here is slope 4. This one will have, that's a velocity of -4 actually by our standards here. Then this is a 6 right here, which is going to be the slope of this line right here, which you can check on a good piece of graph paper. So I'll draw the actual path right here. Whoops. That's the trouble with blackboards. They're very slippery and the gravity is helping them fall. They always fall. There's the return 6, and it will return to this point down here, -3. And then it picks up another 2 units of velocity so that it has 8 units as it returns to the right. Now you might think that this is fortuitous and that I choose any other initial velocity that I wouldn't get such a nice correspondent geometry for all of these collisions. But as you'll see when you do the problem where I ask you to have the thing come in with a unit, something, I think a half a unit of velocity, half the speed of that object. Well, no matter what direction you come in, same pattern emerges. Whoops. Gravity is nasty and friction is meaner. I need something where I can see what I'm doing while I'm drawing. I think that's not right there. And so there is return 8, and then there will be 2 more units added to that, and so forth. Just roughing it out now, but that's pretty close. Okay. So that's the crunch. Now this particular crunch has its mirror image part to it that isn't completely drawn there. But here is a typical case where I brought it in at a velocity of -0.2. Same thing. Only now they're the original lines for this drawing we're doing here. The other lines will lie in this coordinate system. It's very weird sort of, well, I call it a fractional or a fraction coordinate system. Basically, we're talking about what happens when I change the space allowed for a colliding particle from delta x equals 3 to delta x equals 2 to delta x equals 1.5 and so forth. Well, the wonderful thing, of course, is that, and this is something we had proved already when we talked about the kinetic theory of a potential. And that is that this velocity here is some constant over the distance allowed to it. That is the space allowed, delta x, and the velocity allowed, which if mass is equal to 1, classically would be delta p, that this is a constant. Now, that is analogous, believe it or not, It is very strictly analogous, in fact, to the Heisenberg uncertainty relation. This is something that is called action. When you have momentum times distance, that's the quantity is action. And action is quantized. That's because it's a wave-like phenomenon. Does that, has to fit an integral number of steps. So what we're looking at is, sure, Boyle's law of a one-dimensional thing, but more to the point, we're looking at the actual wave nature of matter, just in a very simple situation where, as the decreasing space goes down by a factor, the speed will increase by that same factor. So you'll end up with equilateral hyperbolas if you do it in a balanced way. We're just doing one side here. And I find that good food for thought. This is, something the conservation of action in certain systems is something that's very much a part of classical mechanics, very much a mystery at the great Solvay conference, when the creators of relativity and quantum mechanics, Einstein, or Born, even de Broglie, I think at that point, came and argued about what it is you can do to an oscillator, a pendulum, say, when you change its parameters, when you parametrically amplify it. And the object that they had in mind is a very complicated one that we'll deal with in Unit 4 a little bit, and that is a pendulum whose length is adjustable. So they imagined a pendulum. They had great fancy European-style pendulums hanging from the ceiling. So just like Galileo got fascinated by the church pendulums, these new modern physicists got fascinated by the pendulums in the hotel. And the object was, if you had a man up above holding onto the cable that supported the pendulum, could that man change the pendulum's phase space motion by pulling randomly on the pendulum? Now, it was understood that he would do that fairly slowly compared to the motion that the pendulum was singing. And what they were thinking of was their quantum states they'd been deriving using action principles. That was the only thing they had at the time. Schrodinger hadn't written his equation yet. So the way they got quantum mechanical solutions is by satisfying action equal an integer, basically, times the Planck constant. And the idea was, if you have a variable situation for a wave function, and you start playing with the parameters, say it's an oscillator, and you make the parabola steeper or less steep, that's the parameter k of the Hooke's law for the pendulum. If you're varying that, would that quantum state stay in that quantum state, the quantum state that had a certain amount of action? And they finally decided, yes, it would be very reluctant to change to another quantum state. And that meant that quantum stationary states were very stable in a whole range of systems. That was kind of the conclusion, one of the conclusions that resulted from thinking about that. Well, this is an even simpler model than the pendulum, and it's showing it right away. If they had maybe had this, it would have closed the argument and they could go home earlier. Goodness knows what they would have missed by doing that. In any case, here is the simulation of that, showing that since we're short on time, I won't actually run it, but you can do it. It's one of the scenarios at the very bottom. And you can see there's a 1 over delta x equals delta p. I should say constant over x equals delta p. The constant is a classical number. We're thinking of things that are in joule seconds here. The system that you would have a quantum mechanical one would be some integer numbers of h bars, which is 10 to the minus 34 joule seconds. So you have to realize that these people are taking a tremendous step in thinking about things that so incredibly small that this would happen. So this double monster mash here is just a symmetric recurrence of this thing. And what is interesting about it, this is the actual geometry being played out from that construction that's on this screen here. The actual thing that is described in the text, this is the basic triangle geometry that all of these trajectories will have. And at any time you can draw a line through intersections and just have a copy of this. And that's because when you do that, you're effectively changing the gauge, but let's just say you're boosting to a higher velocity of this thing, and you have the same structure inside here as you have inside there, scale. And that's also explained in the text, and I would have you, sort of forcing you by the problem that this generates to do that. So,
Dr. Harter?
yes.
Sometime later in the course, would we be revisiting these problems algebraically, like some of these problems when you develop other techniques?
Say that again.
Like later in the course,
Mhm.
would we be revisiting some of these problems algebraically?
Exactly. Yes. I mean, we definitely want to revisit this principle of action. That's really important. We'll do that actually before we're out of this review unit. I want to get to action because it should be there in our minds along with momentum, energy, velocity, position, time. It is a player, a very important player. In classical mechanics, if it, I hadn't even discovered that waves were making it, it would be a mysterious quantity. Once you get the waves going, it's a very obvious, more obvious object of thought. But I would like to show you before we go, we're just right now at 5, I would like to show you, if I can pull it up on this computer, which will be fast enough to do it, I would like to show you the tiny Big Bang, which has this structure. What we're going to be looking at is a movie of a wave function that starts out very narrow at the bottom of the time thing. This is time going up. And it expands. You can see it, expanding right here. Forget about the things that are below that point. We'll explain what has happened there. Actually, something has crunched and now it's expanding. This is the Big Bang of a single wave on a ring. Not much of a universe, but it has some structure. And it's the structure that we've just drawn on the board there. These are the zeros. The white is the zero of the real part of the wave. In fact, it's the zero of the amplitude too. So all these crisscrossing lines have, because of Bohr's quantization, integer values of slope. That is, their velocities are quantized. And they're quantized in just such a way they make a diagram like that. And I will attempt to show you that by, I hope, clicking on this, and it should start. Let's see if it does. Yes, there it is. I'm going to pause it just briefly. Now, I don't know if you've noticed, this is a picture of the ring, and look at it when I start at time equals 0 and then pause. Pause. I didn't get it. Okay, time 0. Start it over. It's getting mad at me and won't respond here. Set time equals 0. Pause. There. Okay. Yeah. It's one of those things where it responds later, and then I wanted to see if I could get the minimum uncertainty wave showing there. I gotta kill the pause and then set. There we go. That's about the best I'm gonna be able to do with that. it started out this wide, and it's, essentially zero, very close to zero all throughout the ring except for at the phi equals 0 point. And then, as it goes, it expands. But finally, it meets itself going around the South Pole there. And it makes interference patterns, beating patterns. And you start to see the structure forming. You see the zeros occurring. Where the wave is not is where you should look for information about waves. Where it is sort of nebulous, but where it's not. If it's a particle wave, if it's a very particle-like wave, then you look where it is. And then you do semi-classical mechanics. But this isn't really true quantum mechanics, where the zeros are very prominent and repetitive and fractional. And by fractional I mean, if I can drag this thing over a little bit, there we go. At certain fractions of the Poincare period for this system, and that Poincare period is just the inverse of the frequency difference of the ground and first excited states. The slowest that this thing can oscillate is a period that we're working with here, big T. Time to the next big bang or crunch, which will occur on the opposite side, at the South Pole, which is at the ends instead of in the middle. Isn't this amazing? If only Bohr could have seen this. And you see there's peaks in the wave functions of the dark purple, and there's one right there. These are all reflections of these peaks. Yeah.
What are the bright spots in that pink background, the violet background?
The white?
Yeah, those discs, white discs.
Well, look what it means. It's a zero, see? And we're about to get a really big zero all over, zero everywhere. And the darn thing is peaked on the bottom. The whole thing recurred. You see, this is a periodic system, absolutely periodic. The Bohr's quantum model is absolutely periodic. I'm going to pause it. So your white is where the zeros of the wave are located. And this is a rough plot. We're doing a very rough plot because we don't want to waste time making the whole thing. So this has a wonderful, and let me go ahead and show you some things about these quantum fractals that is characteristic of all fractals that are coming out in classical physics as well as quantum. There's another picture of it that we made a long time ago. Just remember that this is the Bohr ring opened up. This is. Here we actually see the plot, a rough plot of it, quick plot of it. Okay, so what it's doing is going from, and stopping at various places with things of various symmetries. All the symmetries are all playing at once, and they all get their day in court, so to speak. At certain fractions, like 1/3, you'll see 3 peaks. At certain other fractions, like 5/9, well, 9ths is not prime, so I mean it's odd, so I actually do get close to 9 things at that moment. There would have been 11 right here, if you can count them. You can see there's 11 bumps across there. So it's basically going through and telling you about all of the rational fractions that exist within its energy that you've given it. The energy that you've given it is determined by the Fourier components, that is the amplitudes that I have given each of the quantum states. 5 and -5 get that much, 10 and -10 get that much. And the reason we picked the Gaussian is because if you do that, it's the invariant of the Fourier transform. The Fourier transform, which is space-time, here will show Gaussian-like bumps and more clearly delineate these fractal lines on the space-time plot. So this is more food for thought that just comes out of this absolutely crazy idea of a quantum Big Bang. The tiniest Big Bang I can find is right here, being done with the waves that we know and love, but don't understand very well, that are called quantum waves. Now, the rest of this discussion is trying to make sense out of those lines. If you just put down what quantum mechanics requires you to have quantized velocities, so that means you have the periods that are quantized inverse, basically all of the fractions. So you can actually go through those fractions. Just think of a fraction with a certain quantized slope, and it's going to repeat and repeat 1, 2, 3, 4 over some denominator that's integer. Okay, these fractions, numerator over denominator, are being laid on top of each other for all values up to about 11 or 12. That's the extent of the energy I've given this thing. That's how fine I can go when I do that. And then as they intersect,